I love robot combat. Back when I was 14, I first discovered it through Robot Wars that was finally aired in Australia on Channel 10, where I would watch these machines beat the living daylights out of each other in a specially designed arena, and it really got my attention because not only was it super exciting and cool, but it's something that I felt I could get into because I'm not big on sport, but I like to build and design things. So the idea of designing and building this machine that was put to the ultimate test in the arena in a 1v1 fight really appealed to me, and I'll be honest, I got pretty addicted. For the next 4 or 5 years onward from that point, my whole life revolved around robot combat. I competed in local events, I flew interstate, I would design robots on my exam papers because I couldn't care about the class, but I wanted to build robots. And the really neat thing about combat robotics is it's a design challenge and you learn all sorts of things. I learned 3D modeling, I learned electronics and wiring, and how to build things that could withstand incredible punishment. And it was those design skills that got me eventually into industrial design at university and proved to be an incredibly valuable foundation for where I am today. But that was over 10 years ago, and after a while I stopped competing and started instead commentating on events, and it's been a good 5 years since I last competed in a combat robotics tournament, because there's been a few factors involved. But that all changes today. There is a combat robot event happening in Adelaide here in Australia in August, and I am determined to compete. And I'm going to take you along for the journey. There are several weight classes involved, and I'm going to be building a robot for every one, starting with this video, which is going to be walking you through how to build a fully 3D printed antweight to complete in the non-destructive antweight class. Let's get started. Okay, so before I begin, I want to get one thing out of the way. Combat robots aren't really robots, and this upsets a lot of people that we call them robots, but the thing is, they're not autonomous. Now, there's nothing stopping you from making an autonomous killer combat robot, but for the most part, these machines are remote controlled. So think of them like a remote controlled car or remote controlled plane, but with armor and weapons, and they compete in a specially designed arena. But there is rules, so there's weight classes and there's rules for combat. The rounds go for 3 minutes, usually, and the idea is to incapacitate your opponent in those 3 minutes by either destroying them completely or flipping them on their side or otherwise getting them to be unable to move, then they get counted out. Now, you can't have projectiles or explosives or liquid weapons or EMP jamming weapons because A, the safety of the audience is really important, and B, something that just jams a radio so you can't control the robot isn't really that exciting, is it? So there is rules that basically make it a bit like medieval combat. You can have things that whack, slash, flip, cut, but you can't have anything that could endanger the audience or make it boring for them watching. And just like boxing, there's weight classes. So the ones you see on TV are heavyweights. These machines weigh over 100 kilos and they are massive, they're huge, they're expensive to build, and they are so incredibly dangerous now that they compete in only a few specially designed arenas around the world. And even then, battlebots, for example, has had to put limits on weapon tip speed recently because of just how destructive these machines are. They are the big boys. These are the little boys. Right at the other end of the spectrum are antweights. These machines weigh 150 grams. Max. But in that weight limit, you can still have a lot of fun. These machines are easy and cheap to build, they're lightweight, you can transport them easily, and you can build them out of everyday materials. Now, this is FLS, this is over 10 years old. I hung on to it because no one was able to destroy it. It's built with a paint scraper wedge with some wheels and some bits of chopping board armor on the side. I built this from scratch in my parents' basement workshop when I still lived there, and it did really well. It actually won its first event. But these days, I do a lot of 3D printing, so I want to rebuild this machine using 3D printing processes, and I'm going to release the files to you guys so you can build your own as well. But what goes into building a combat robot anyway? Well, some of you may remember last year I made this. This is one of my off-road platforms that I designed to test wacky wheels, like the wobbly wheels on that. And this is essentially the same as a basic combat robot. It uses all the same components, and it's very easy to put together once you know what's involved. It has motors, it has speed controllers, it has the receiver, and it has a battery. And those are the core components needed to get something like this moving under remote control. Let's go through each of those components individually. These are gear motors, and you need them for your machine to move. Without them, it's just going to be sitting there unless you figure out some sort of crazy walking mechanism, but yeah. I would start with motors, and there is a huge range to choose from. I usually look on eBay to find low-cost gear motors that I can use for my robots, but you can go all the way to custom-designed, specially made combat robot gear motors that are hardened, which means they're much more durable, and everything in between. So for example, here I have these little 1000 RPM gear motors from eBay. They're rated for 12 volts, which is a good voltage to go for combat robotics using a 3-cell lithium battery. Now the really cool thing about combat robotics is even within the rule set, there's a huge scope to make it your own. As long as you're within the weight limit and you're not violating the rules, you can really do what you like. And choosing your gear motor is a good example of that. You can choose a really small gear motor, which might be lower power, but give you more weight for a bigger weapon or more armor, or you might choose a much larger, more powerful gear motor, but that's heavier and therefore it's going to need a bigger battery, use more current, and take up more of your weight limit. And it's all this sort of balance of finding the best for your design and working with that. Now in terms of the output RPM, I would say you want to go for something between 500 and 1000 RPM in terms of the output speed. And you want something that's not too small. For antweights, you can use these really tiny little gear motors, but I also really like these ones. And if you want to go super hardcore, these ones from UNAVAILABLE, these are great for beetle weights and even a little bit larger. They're very expensive, but these are very, very durable and very high power. So there's all sorts of things in between. I just recommend starting on AliExpress or eBay. And again, I'll try to put some links in the description for good gear motors you can start with. Now, just before I move on from gear motors, there's two different types of motors you need to be concerned with: brushed and brushless. Don't use anything that are stepper motors. They're completely unsuitable for combat robotics. I would recommend starting with a brushed gear motor, and then you can use a brushed speed controller. So let's talk about speed controllers next. This is a 2-in-1 speed controller that I picked up from FlipSky. This is what I'm going to be using for my build, and it controls 2 different motors using 2 inputs from your receiver. Speed controllers come in all shapes and sizes, and you want to choose one that's suitable for your motor. They can be tiny like this, in which case they're suitable for a small little motor, or they can be massive like these guys, which I used on the remote control lawnmower build I did with I Did a Thing. So these guys are really large and they're rated for 85 amps. And I use them to control those wheelchair motors on that build. Usually when you buy your gear motor, the listing will show on the datasheet the stall current for that motor at the rated voltage, and that's a good way to size your speed controller. If you go too small, you might blow up your speed controller, and if you go too large, well, you're wasting space. I'm not going to be putting this into my antweight, which only can weigh 150 grams, am I? I'm going to be trying to size it for something like this. So for my build, I'm going to be using the FlipSky speed controller because, again, they're cheap and they are a 2-in-1 deal, so I don't need a single controller for each motor, which adds wiring complexity. I can just use the 2-in-1. Next up, you need a way to power your robot platform, and for that, you need a battery. So these are lithium polymer batteries. They've become incredibly easy and accessible to get now because of the advent of all sorts of like remote control aeroplanes and things. That's what these ones are specifically designed for. And they come in all shapes and sizes, from little tiny ones to much larger ones to massive ones that have a ton of capacity. So when I say capacity, how do you measure how much capacity a battery has? Well, it's measured in amp hours, and these batteries are rated for milliamp hours because they're usually much smaller than 1 amp hour. So this little battery here, 300 milliamp hour, that is more than enough for an antweight robot. Remember, they only have to run for 3 minutes at a time. And this, unless you have a very high-powered drive system or weapon, then 300 is more than enough for an antweight. To charge this, I recommend the low-cost chargers that simply plug into this balance lead, and then they charge it over a period of time. Now, I do need to say, with lithium polymer batteries, they can catch fire. There is an inherent safety risk with them because of the lithium inside. When they do catch fire, you can't really put them out. So to use them safely, you need to make sure they are fully well enclosed and cannot be damaged. So they are actually soft. They're not hard. There's no hard case. So you need to be responsible for making a hard case around them to protect them. When you draw too much current out of these or you discharge them too much, they can become what's known as puffy, where they actually will puff up from gas inside the cells as they deteriorate. When a battery goes puffy, it's bad. You need to replace it and throw it away. And there are very specific ways to safely dispose of lithium polymer batteries. Again, links in the description for everything I'm talking about. So in summary, with lithium polymer batteries, make sure they are not pierced or damaged, make sure they don't short circuit, and make sure you don't discharge them too much, because then they can't fully recover and recharge. So again, 300 is good, but don't just keep running fights till the robot stops working. Recharge it after every fight with your cheap battery charger. And I also recommend, when we have this at robot events, a bucket, a metal bucket with sand in it, because again, if these catch fire, you can't put them out. All you can do is bury them with sand, put them outside, and wait for them to finish doing their thing. So with that out of the way, let's move on to how to control your robot. Controlling your combat robot is the same as any other remote control vehicle. You need a radio transmitter and a receiver. This is one designed for like aircraft and drones, and it has multiple channels, but you can use almost anything on the market as long as you have the appropriate receiver to receive those commands. And just like everything else I've talked about, receivers come in all different shapes, sizes, and flavors. This one here is 6 channels. So for example, for a remote control aeroplane, you might use this for throttle, ailerons, I'm not exactly too sure on the terminology, but you have 6 different inputs to choose from. But if you have a transmitter suitable for a remote control car, it may only have 2 channels, which again is suitable for a robot like this with only drive, but you have no way to control a weapon. And when you're building antweights, size and weight again is very important. So although this is a 6-channel receiver, this is also a 6-channel receiver. And yeah, they both do the same thing, but this is microscopic in comparison. Much harder to wire in, but it does exactly the same job. So when you're choosing what you need, keep in mind the size of the receiver and how many channels you need for your machine. And then there's also things to consider like mixing. So for example, these drive like tanks. It's called differential steering, where both wheels go forwards with the 2 motors working together, but to turn, they actually go in opposite directions. So that means to control this properly, you need to mix those inputs, and it's known as V-tail mixing or tank mixing. So many transmitters will actually offer it because it's used in some aeroplanes, but also the 2-in-1 speed controllers like this one from FlipSky actually offers vMix built into it, so the transmitter doesn't even need to do it because this thing can do it for you. And you can also buy separate modules that plug in between your speed controllers and receiver to do that mixing. But keep that in mind, because your robot has tank style steering, you need mixing somewhere in the mix to make it all controllable. And really, that's the core of what you need to build your combat robot. Now, there is other things like your plugs. You need a switch of some kind to turn it safely off and on. And also, I recommend a scale. This is just a kitchen scale. This is great for all the insect class robots like the antweights and beetleweights, because again, you need to make weight. It can't be overweight. It's like boxing. You cannot compete unless you're within the weight class. So I use these scales all the time to weigh up components and get an idea of how heavy the robot is before I then take it off to compete. So I think it's about time we design up a version 2 of this little wedge robot so I can then start drawing it up in Fusion 360. Before I do anything in CAD, I always start with a sketch. And what I really like to do, and it's really practical, is just to get your components and sketch them out on a piece of grid paper. This really gives you a real world idea of what shape and size your combat robot should be, and just where the parts can be in space. And as I said, I used to draw this sort of thing all over on my exams and just when I was bored to get an idea of how to arrange these parts and Tetris them in such a way that I could build the most compact design possible. And this is really the best way before you get into CAD, because if you start with CAD, you'll limit yourself. But if you start with pen and paper, you'll come up with some really cool ideas that you can then translate into 3D design and then create really cool robot concepts out of them. And it's only after I've done some designs on pen and paper that I finally come into Fusion 360, and to get an idea of where the components are in space, again, I do a single sketch, and I do something like this, where I'll measure my components with calipers, make sure they're precise, and then bring it into a single sketch to get an idea of where they might sit before sketching anything more complex in 3D. Because again, it's really easy to lose yourself in 3D space and then design something that's too small or where the parts won't fit. But by designing in this order, I feel you're much more likely to end up with a design where the parts actually fit together and your final print isn't going to be too small, and then you'll have to go back to the drawing board. Okay, I got a little bit carried away. As usual, it's now nighttime. So I'll just walk you through a few of the design approaches I use, starting with the shelling approach. So let me just hide the top body here. What I've done is I designed it solid, and then I used the shell command to hollow it out. And what's really neat about that is if I go back to the shell, I can change the amount, and that can be changed to make it lighter and suit a more detailed printing process like SLS or MJF, I think it's called, multi-jet fusion, where you can get away with like a 1.5 millimeter thick wall. But with FDM, I'm probably going to go with 2. But let's say I want it to be even thicker, I could say like 3. And I can update that as follows. And then my whole timeline updates with a thicker wall like that, but I'm happy with 2. I think that'll print fine. And obviously you need to get into the robot, so I've got this top panel here. And to make that top, I use this surface body. So I use the surface workflow to draw this body, which then I use to cut into that shelled shape to remove the top section to make it a separate part that then I could use as the lid. It's got some details for screws to hold it in place, a little hole for the LED, and my logo. It's interesting to see just the tops of those spikes because it happened to intersect with them there. And I can change that if I like, but it's actually looking pretty cool to me. The only issue is some areas will need a lot of support material. Namely, if you look on the side, the bottom area will need support. And also this area here, where I am allowing for that top to be screwed into place, needs support. Now I could go through and design some angles and chamfers and all sorts of features to bridge and whatever, but it's fine. I'll just send that with support material because I can easily access it. I can pull off the bottom and pull off those areas, and then I can put it together. So let's export this and then open it up in Prusaslicer. I almost forgot this, so I just switched to the latest alpha Prusaslicer 2.5. I can't keep up. But the reason I've done that is because there's this new setting which is called Arachna. I don't know how you pronounce it, but it can change the extrusion width intelligently to avoid doing those little small fills that usually jump around and take ages and don't look that great on the print. So I've just switched across to that. It hasn't changed the print time too much, but if you zoom in, you can see how the lines actually intelligently change width to perfectly fill out the different wall thicknesses of the print. It's really neat. So yeah, here's the idea. It builds up, got the big scoop, comes up, builds the motor mounts, and comes all the way up. I've got a little bit of allowance for the top of the holes to droop down because in my video ages ago about printing accurate holes, this is a good little trick to do like a teardrop. Then it comes all the way up like that, and it's good to go. So let's send it to the printer. And here it is. This is the first test of the plastic antweight frame. It came out pretty good. It's on the longer LK5 Pro that I've heavily modified with a G10 print surface and lots of other tweaks. But then that takes us to the next stage. How do you wire in all of these pieces together so you get a working combat robot? Let me show you the wiring diagram. So here we have the wiring diagram for my combat robot, and you can use this for all sorts of different remote control applications, but as I mentioned, you can get quite a lot more complicated with your combat robots. This machine doesn't have any weapons or anything like that. It's just drive motors with a combined dual speed controller, which makes wiring a heck of a lot simpler, and you can get much more complex than this. But this is a great place to start, and let me just step you through it. We have our 2 motors, M1 and M2. We have a battery down here, which is going to be the lithium polymer battery. My one is 2 cells. And then I've got the speed controller. So this is the dual speed controller. ESC stands for electronic speed controller. And a dual speed controller can control 2 motors at once. Without this, we'd have to have individual speed controllers per motor, which is exactly the same idea, but it means you'll have to split off the wires from the battery to each controller, and it just adds a bit of complexity. So having it in one makes my life a lot easier. Then we have the receiver, RX. This is what controls the robot remotely. So I use the transmitter to send commands that the receiver then picks up, and these little yellow wires are the data lines per channel, and they might be white or orange on your particular controller. But essentially what that means is the receiver receives commands that it then gives to the speed controller, then the speed controller will then relay those commands into movement in your motors. Now there's 2 other additional components in this wiring diagram that I haven't really talked about before. That is a switch and a light. Now within the rule set, your robot must have some kind of visible power light to let everyone know that it's on. This is for safety, and also helps you identify if the robot's had its battery or electronic system kicked out, because the light will go off, you can't move it, then you realize, okay, it's dead. So I recommend just a simple LED. These are really cheap these days. I'm going to use a 3mm ultra bright LED. And then you need a suitable resistor. Now there is a very, very handy calculation that lets you size the resistor for the battery voltage, which will then allow enough current to run the LED without blowing it up instantly. Because if you just put the LED straight to the battery, it's going to have too much current and then it's just going to explode. Because these are diodes after all. They're LEDs, it stands for light emitting diode. So here's the calculator I've used for mine. I'm playing it really safe with a low current. So the LED might not be as bright as it could potentially be, but it'll be more than enough as an indicator light for this robot. And then finally, you need a switch. This is really critical, because you need to turn your robot off and on again. There's different types of switches you can use. You can buy special battle-hardened switches that use an Allen key. I highly recommend getting one of those if you can, because they're really safe and easy to turn on and off, yet they're very durable. They won't turn off during combat. And yeah, that's essentially it. This is the core for every combat robot out there. You just will start to tack on things like weapon motors, weapon speed controllers, different battery systems, and more stuff like that. But if you can master this, you're well on your way to learning how to build combat robots, or any remote control platform for that matter. There is one final thing I need to talk about before I move on to wiring my robot, and that is your BEC, or battery eliminator circuit. The reason I didn't show it in my wiring diagram is because my speed controller has it built in. So what a BEC is it allows your receiver, like this, to receive 5 volts, usually 5 volts, to be powered. And obviously your battery isn't usually going to be 5 volts. Like my lithium battery is 7.4, it might be even higher. And you need something called a BEC to regulate that down to a safe 5 volts so this can get power. Now, as I said, this speed controller actually has a built-in BEC, but it's not powerful enough to run external systems that might be current hungry, like a servo motor or something like that. It's only powerful enough to run the receiver. So if you want to have some kind of servo motors or larger current hungry components attached to that BEC output, that 5 volt output, you may need a dedicated BEC that has a larger amount of current capacity to then run those systems. Now it comes to the most fiddly part of all, assembling and finishing your little combat robot. Now, there is no hack for this. It is tedious and fiddly to put together these little robots. You need to be quite confident with your wiring and quite decent at soldering. I can't teach you how to solder in a short video tutorial, unfortunately, but with practice makes perfect. So what I like to do is just try to shovel the parts in as tightly as possible and get an idea and feel for where they'll sit. And you'll see already that wires take so much space up, way more than you'd ever expect. By far, the most fiddly part of this build is the switch and LED, because this needs to not only turn on the robot's power, but also give power to the LED light. And if you don't have this, then as I mentioned before, it's a safety hazard and you're probably not going to be allowed to compete. You must have a safety switch and an LED, but it does mean you need to do some pretty fiddly wiring. So I have this little trick, this little hack that I use to combine 2 wires into one, which you do need to do if you need to split power off between 2 different systems. I like to use a little zip tie to hold the tinned ends together of that wire, which gives you a little bit more freedom to hold them in place with another hand and then solder them into the position. Without this, you're kind of holding 3 things at once as well as a soldering iron, and it's kind of impossible. But by using the zip tie, you can manipulate them as one, and I do really find it helps you get them to position, because again, it can be really fiddly soldering together these components. And then at this stage, it's a great idea to do a test run where you plug the receiver in and get an idea of which direction the motors will spin. Even after doing this for so long, I never get it right first go. It always takes a few tries to figure out what channel I'm using and which direction the motor should spin. So I highly recommend doing this while the machine is open and easy to access, so you can perhaps swap the wires on one of the motors or easily swap the channels on the receiver to make sure the robot is moving in the right direction before you button the whole thing up. Because this robot's so small, I opted to use hot glue to secure the gear motors in place. It's not the most elegant solution, sure. I could have done a little faceplate with tiny little screws, but because they're just so small, it made more sense to me to use a little bit of hot glue and then hold them in place like that, and there's nothing wrong with that. Because yeah, it's highly unlikely it's going to be perfect off the 3D printer first go. You're going to need to do some modifications, drill a few new holes, file a few areas, and with that, I carefully jam the guts in and secure the top lid in place with 4 screws, and our little 3D printed antweight is complete. And here he is. This is my fully 3D printed combat robot antweight. And yes, I got a haircut. Who needs continuity anyway? So for the most part, I'm really happy with this design, but there's a few issues that need to be remedied. Number one, it's overweight. Now, remember I mentioned using a set of kitchen scales is like critical for getting these robots within the weight class, because if you're overweight, you can't compete. Well, this is about 30 grams over the weight limit. It's about 180 grams when it needs to be 150. That's mostly because 3D printing is a lot heavier than I expected, and it also is due to the very heavy gear motors that I've chosen. The previous version had these much smaller gear motors that are a lot lighter. These ones are quite a lot heavier, more powerful, but a lot heavier. So I think to make this under the limit, I'd either have to make the frame a lot lighter, which is definitely something that's possible, or go to the smaller gear motors. But again, I'm going to leave that in your court because it's your design and you can adjust it and work with it as you like. If you're not planning to actually properly compete, you should still build it as is, because it's really a great learning experience for how these machines go together. And if you have two of them, they'll be equally matched anyway. And I also ended up going with this little toggle switch at the top. You can see that really bright green LED looks really good there. I had to move the position, hacking it as I'm going, because the switch is quite large inside and those wires take up so much space, I always forget. But I actually quite like the idea of the switch being vulnerable, because if these two were fighting and there was two of the same, then that switch, it's off. So I kind of like the idea of them competing and trying to defend that switch. I didn't end up using the combat robot switch with the key, the Allen key that turns them off and on, but I'll use that for my next version that I'll actually compete with, because I need to make it, again, go on a diet. And one final thing I need to address is that the speed controller I've chosen from FlipSky doesn't have braking. It's not a huge issue, but it does mean this is a little bit harder to control than using some of the other speed controllers like the ones from BotBits that I've used in my previous antweights, because when you turn and release the stick, those speed controllers brake. They'll try to stop the motor. This current speed controller doesn't. So when you're going forward and back and turning, it's not a big deal. But if you're trying to spin on the spot, it makes trying to locate and line up the robot towards a direction quite difficult, because it will spin more than you want because it's not stopping and braking in the precise position. If you'd like to build one of these robots for yourself, you can find all the resources in the video description below. And in the next video in this combat robot series, I'm going to be building a beetle weight. These are 1.36 kilograms, so a little bit larger than this. And I'm going to be rebuilding an old design I had called Fugu. And I'll let you try to figure out why it was called that. But till then, thank you so much for watching, and thank you so much for being patient with me in these unprecedented times. And I look forward to seeing you again very shortly here on Maker's Muse. Catch you later, guys. Bye.